Somewhere in our galaxy, right now, a dead star is slowly turning solid. Not because it has cooled down. Its interior still burns at millions of degrees, hotter than the core of most living stars. And yet, inside that impossibly dense corpse, atomic nuclei are locking themselves into a crystal lattice. Freezing not from cold, but from pressure so extreme, it rewrites the rules of matter. Scientists call these objects diamond stars, cosmic gemstones the size of Earth. But that description is only half true, and the reality is stranger and more beautiful than any jewelry metaphor can capture. Tonight, we go into the heart of a crystallizing white dwarf to find out what really happens where extreme heat and true solidity coexist in ways nothing on Earth ever could. Before we go any further, if you enjoy these deep dives into the strange corners of the universe, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Picture a star that died billions of years ago. Its fires are out. It has stopped fusing anything. It has thrown off its atmosphere, blown away its skin, and shrunk into a naked ember about the size of Earth. And yet that ember contains almost as much mass as the sun. Squeeze that much matter into a ball, as small as our planet, and you get densities that no laboratory on Earth can produce, no rocket can survive, no imagination can casually picture. In that impossible interior, temperatures are still measured in millions of degrees. The gas inside is not gas as you know it. The atoms have been crushed until their electrons no longer belong to any particular nucleus. Everything is naked, everything is packed, everything is glowing. It's the corpse of a star that refuses to fully die. And here is the strange part. That corpse, still burning hot at its core, is quietly turning to stone, not slowly cooling into a lump of solid ash, the way a coal on a fire turns black. Something stranger. Deep inside that dense interior, the atomic nuclei are lining themselves up into a rigid lattice, snapping into an ordered geometric pattern the way ions do in a crystal of salt or a chip of quartz. In the center of a white dwarf, an ancient plasma is freezing without ever getting what we would normally call cold. That is the paradox we are going to unwind tonight. To do it, we have to build the stage carefully. We have to understand exactly what kind of object we are looking at, why it exists at all, and why the very rules of matter get bent inside it. Because the story of a crystallizing white dwarf does not begin with the crystal. It begins much earlier, with a very ordinary star running out of the one thing it needed to survive. Take a star like the sun. Something roughly the same mass, give or take a factor of a few. For most of its life, such a star does exactly one thing at its core, over and over, for billions of years. It fuses hydrogen into helium. Deep in the middle, where temperatures reach around 15 million degrees and pressures are unimaginably intense, 4 hydrogen nuclei are pressed together by gravity until they merge into a single helium nucleus, releasing a tiny burst of energy each time. Multiply that tiny burst by an astronomical number of reactions per second, and you get the outpouring of light and heat that we call sunshine. That fusion also does something quieter, but just as important. It holds the star up. The energy pouring outward from the core creates pressure that resists gravity's endless attempt to squeeze the star into a smaller and smaller ball. Fusion is not just the star's furnace, it is the star's skeleton. But hydrogen at the very center does not last forever. Eventually the star burns through the hydrogen in its core, and is left with a ball of helium ash where its fuel used to be. Fusion in that inner region stops. Gravity, which never rested for a moment, seizes its chance. The core begins to contract. As it contracts, it heats up. Because compression always heats things up. That heat pushes outward into the layers around the core, causing hydrogen fusion to ignite in a shell around the dead center. That shell burning dumps enormous energy into the star's outer layers, and the outer layers respond by ballooning outward. The star bloats, it reddens, it becomes a red giant, swollen to hundreds of times its original size, a bloated furnace glowing dimly and orange because its surface has cooled even as its interior has become more violent. Inside this red giant, the helium core keeps contracting and heating until it crosses a new threshold. At around 100 million degrees, helium itself becomes usable as fuel. 3 helium nuclei begin to slam together to form a nucleus of carbon. This is the birth, in the belly of a dying star, of one of the most important elements in the universe. Some of that freshly minted carbon does not stay carbon for long. Another helium nucleus arrives, fuses onto the carbon, and produces oxygen. 2 of the most important elements for planets, chemistry, and eventually for you, are being cooked out of pure helium in the core of a star that is coming apart at the seams. For a star like the Sun, this is the end of the fusion road. It is not massive enough to squeeze its core hard enough to fuse carbon into anything heavier. When the helium runs out, the party is over. What is left in the middle is a ball of carbon and oxygen, still incredibly hot from the abuse it has taken, but with no way to generate any more energy. The outer layers, meanwhile, have grown so distended and loosely bound that they begin drifting off into space, forming a shimmering shell called a planetary nebula. This has nothing to do with planets. It is just an old-fashioned name from an era when small telescopes made these glowing shells look like faint, fuzzy disks. What matters for us is what stays behind. The gorgeous nebula fades and disperses over tens of thousands of years, but the naked core, that dense ball of carbon and oxygen that once sat at the star's heart, does not go anywhere. It sits there, exposed to the universe, roughly the size of Earth, glowing white hot with leftover heat. That exposed remnant is what astronomers call a white dwarf. If you compare it to the star that produced it, a white dwarf is absurdly small. Our sun measures about 1,400,000 kilometers across. Its future white dwarf will measure only about 12 or 13,000 kilometers across, roughly the diameter of Earth. That is a shrinkage by a factor of 100 in radius, which means a shrinkage by a factor of about 1 million in volume. And yet, a typical white dwarf still contains something on the order of half the sun's mass, sometimes more. Take half the mass of a star, compress it into a ball the size of our planet, and you get an object whose average density is about 1 million times higher than the density of ordinary rock. A cubic centimeter of this stuff, a piece the size of a sugar cube, would weigh around a ton on Earth. And that is only the average. The density is not uniform. It rises steeply from the surface toward the center, because the deeper you go, the more overlying material is pressing down. The core of a white dwarf is far denser than its outer layers, and it is in that hyperdense core that the strangest physics of the whole story will play out. There is an obvious question you should be asking by now. If fusion has stopped, what stops the star from collapsing? Gravity has not gone away. Half a solar mass in a body the size of Earth should be squeezing itself into an ever smaller ball. And yet the white dwarf sits there, quiet and stable, unchanged in size for billions of years. Something is pushing back. That something is not heat. It is not radiation. It is a quantum mechanical effect with no analog in your daily life, and it is called electron degeneracy pressure. To understand it, you have to accept a simple but strange rule from the world of subatomic particles. Electrons belong to a family of particles called fermions, and fermions obey what is called the Pauli exclusion principle. In plain language, no two electrons can occupy exactly the same quantum state at exactly the same place at exactly the same time. Each one has to be a little different from every other one nearby, in position or in momentum, or in some other quantum property. When matter is spread out, this rule is easy to obey. There is plenty of room, plenty of energy states, and no electron is stepping on any other electron's toes. But when you compress matter, you crowd the electrons together. You force them to share the same tiny volume. And the rule kicks in. Since they cannot all occupy the low energy, low momentum states, some of them are forced upward into higher momentum states, whether the temperature says they should be there or not. High momentum means fast motion. Fast motion means pressure. That pressure has nothing to do with heat. It exists even at zero temperature. It is a purely quantum effect, a consequence of the identity of electrons themselves. Inside a white dwarf, this degeneracy pressure is enormous. It is the invisible scaffolding holding the whole structure up. Even as the star loses heat over billions of years, the degeneracy pressure barely notices, because it does not depend on temperature. As long as the electrons are packed tightly enough, they refuse to be squeezed further. Gravity pushes in, the degenerate electrons push out, and the star sits in equilibrium, no fuel required. This is why a white dwarf can keep its size for as long as the universe has existed, and still remain unchanged. Its structure is not being maintained by the combustion. It is being maintained by a quantum rule about identity. But the phrase unlimited does not apply to electron degeneracy pressure, and this is worth pausing on. Degeneracy pressure is strong, but it is not infinite. If you keep piling more mass onto a white dwarf, the electrons have to be squeezed harder and harder, forced into higher and higher momentum states. Eventually, those electrons are moving so fast that they're approaching the speed of light. And once relativity enters the picture, the pressure they generate stops rising as quickly as gravity's demands. Beyond a certain mass, the electrons simply cannot push hard enough. That threshold, worked out by the astrophysicist Subramanian Chandrasekhar, sits at about 1.4 times the mass of the Sun for a typical white dwarf composition. A white dwarf heavier than the Chandrasekhar limit cannot exist as a stable white dwarf. It is doomed to a different, more violent fate, either collapse or thermonuclear detonation. We will not follow that story tonight, because our subject is the quiet cooling of white dwarfs that sit comfortably below that limit. But it is worth knowing that the same quantum trick that keeps a white dwarf standing has a ceiling, and above that ceiling the star's story ends very differently. For the stars we are interested in, the ones safely below the limit, the future is much calmer. They sit as compact glowing remnants, held up by their degenerate electrons, radiating away the leftover heat of their long-dead cores. And this is where we need to be careful about what a white dwarf is actually made of. It is tempting to imagine a pure ball of carbon or a pure ball of oxygen, but nature is messier than that. During the red giant phase, helium was fusing into carbon, and some of that carbon was capturing further helium nuclei to become oxygen. How much of each element ends up in the final core depends on many things. How massive the parent star was, how efficient the different reactions were at various temperatures, how much convection stirred the interior, and how quickly the whole process shut down. The exact ratio of carbon to oxygen in a given white dwarf is not a fixed universal number. It is a fingerprint of that particular star's life story. For most white dwarfs left behind by stars broadly like the Sun, the core is a mixture of both elements, with the balance shifting from case to case. Some white dwarfs are more oxygen-rich, some more carbon-rich, and the exact profile from center to surface can vary, because oxygen tends to be produced more efficiently at the very core and carbon dominates further out. This will matter enormously later when we watch these two elements decide whether they want to freeze together or freeze apart. But for now, the takeaway is simple. When you look at a typical white dwarf from a star like the Sun, you're looking at a dense mixture of carbon and oxygen nuclei, not a single pure substance. There are exceptions worth mentioning briefly, so you do not walk away thinking every white dwarf is the same. Some stars are so small that they never get hot enough to fuse helium into carbon. If such a star is stripped of its outer layers early by a companion in a binary system, it can leave behind a white dwarf whose core is almost pure helium. On the other end, stars more massive than the Sun, but not massive enough to explode as core collapse supernovae, can push their fusion further. Their cores burn carbon, producing oxygen, neon, magnesium, and other heavier elements. The white dwarfs they leave behind are oxygen and neon white dwarfs, denser and rarer. Both classes are fascinating, but the story we are telling here, freezing, latent heat, the diamond nickname, belongs mainly to the carbon and oxygen white dwarfs, which are by far the most common. When we say white dwarf for the rest of this journey, we will mean one of those. Even among carbon and oxygen white dwarfs, the exposed core is not the whole picture. Sitting on top of that dense interior are thin outer layers, remnants of the star's original envelope that were not blown away in the planetary nebula. There is usually a shell of helium wrapped around the core, and above the helium, in many cases, an even thinner shell of hydrogen. These layers are thin compared to the total mass of the star. The hydrogen layer, if it exists, is often less than 1/10,000th of the total mass. The helium layer is thicker, perhaps 100th. Both together weigh almost nothing compared to the carbon and oxygen interior beneath them. But they do something crucial. They form the atmosphere. They are what an outside observer actually sees when they point a telescope at a white dwarf. The blazing surface is not the raw carbon and oxygen core. It is a much thinner outer skin of lighter elements that has been heated from below by the enormous reservoir of thermal energy trapped in the interior. If you were somehow able to peel back that thin skin and look at the naked dense material underneath, you would not see anything like a glittering gemstone at the surface, no matter what pop headlines may have told you. You would see something much stranger, but we will come back to that. For now, remember this. A white dwarf is a small, exposed stellar core, roughly the size of Earth, carrying a substantial fraction of a solar mass. It does not fuse anything. It is held up not by heat, not by combustion, but by the quantum stubbornness of its own electrons. It has an interior made mostly of carbon and oxygen nuclei, with a density that rises dramatically from surface to center, and it is wrapped in a thin skin of helium and often hydrogen that hides its exotic guts from view. and it is unimaginably hot. Or at least, it starts that way. Right after the planetary nebula phase, when the naked core first becomes visible to the universe, a young white dwarf can have a surface temperature of around 100,000 degrees, sometimes even higher. That is many times hotter than the surface of the sun. The interior is hotter still, perhaps tens of millions of degrees deep in the middle. All of that heat is a memory. It is left over from the crushing collapse and the last gasps of fusion that occurred before the star retired. There is no fresh energy source to keep it topped up, which means from the very moment a white dwarf forms, it's losing its heat to space. It is glowing brightly because it is bleeding energy. Slowly, patiently, over timescales longer than the current age of the universe, that stored heat drains outward and radiates away as light. This is what people mean when they say a white dwarf cools. The word is a little misleading, because the interior does not cool the way a cup of coffee cools. It cools while remaining hotter than anything you have ever imagined. It could be cooling and still be a millions of degrees in its core. It is losing heat while still being catastrophically hot, because the reservoir of thermal energy is so enormous compared to the trickle of light escaping through its thin envelope. The atmosphere throttles the loss. The dense interior stores the heat, and the white dwarf becomes fainter and cooler over billions of years, sliding gradually down what astronomers call a cooling sequence, a slow, one-way trip from a young, hot, bright ember toward a very old, very dim, nearly invisible one. And that is where the story we came here to tell begins. Because the cooling of a white dwarf is not a simple, boring process. It is not just a hot ball radiating away its temperature like a stove burner turned off. Something remarkable happens along the way. As the interior gives up its heat, the ions inside it, the naked carbon and oxygen nuclei sitting in a sea of degenerate electrons, do not just slow down. They start to feel each other's presence in ways they did not before. The forces between them, which had always been there but had been overwhelmed by chaotic thermal motion, begin to matter more and more. At some point, deep in the very center where the pressure and density are highest, those forces start to win the argument. The chaotic dance of the nuclei becomes less chaotic. Order begins to sneak in, and a phase transition of a kind that does not really exist under Earth conditions begins in the belly of the dead star. To see how that phase transition works, and why it can happen while the interior is still glowing at temperatures that would vaporize any known material on Earth, we need to go inside a white dwarf. We need to look at what the material there is really like, because your intuition for solids and liquids, built from experience with ice cubes and molten metal, is going to fail you at every turn. What we are about to enter is not a rock. It is not a liquid. It is not a gas. It is something much stranger, an ocean of ions and a sea of quantum mechanical electrons, packed together at densities that make LEDs seem as thin as air. To understand how such a thing can crystallize, and why the crystal is nothing like anything you could hold in your hand, we have to open the door and step into that ocean. Imagine yourself shrinking down to the size of an atom and being placed somehow inside a white dwarf, not on its surface but deeper, several hundred kilometers below the thin outer skin, in the region where the density has already climbed to levels that no laboratory on Earth can reproduce. What surrounds you here is not gas, not liquid, not solid, at least not in any way that matches your intuition. There is no air to breathe, no rock underfoot, no clear boundary between one substance and another. What surrounds you is an ocean without a shore, made of particles that have forgotten how to be atoms. Above you, only a few thousand kilometers up, sits the outer envelope. A thin veneer of helium and possibly hydrogen that hides everything down here from the outside universe. That veneer is where the visible light comes from. The atmosphere of a white dwarf is what a telescope sees glowing white or blue-white in the night sky. But the atmosphere is a paper-thin lie draped over the real body of the star. Down here in the interior we are exploring, the composition is different, the physics is different, the very concept of an atom is different. To understand what a crystallizing white dwarf actually crystallizes, we have to look carefully and patiently at the material we are floating in. Start with the nuclei. In ordinary matter, the kind you're made of, an atomic nucleus is surrounded by a cloud of electrons that belong to it. Those electrons occupy specific orbitals, follow specific rules, and give the atom its chemistry. It is the electrons that decide whether carbon will bond with oxygen, whether iron will rust, whether water will freeze. Chemistry is a story about how the outermost electrons of atoms interact with each other. Take those electrons away, and there is no chemistry left. There is only nuclear physics and electric force. Inside a white dwarf, the electrons have been taken away. Not literally removed from the star, but stripped from any particular nucleus. The pressures here are so enormous that no atom can hold its electrons close. The moment an electron tries to settle into an orbit around a carbon or oxygen nucleus, the surrounding matter squeezes it out. It gets crushed into a common pool shared by every nucleus around it. What used to be a discrete atom is now a bare, positively charged nucleus, floating in a sea of negatively charged electrons that belong to no one in particular. This state is called a fully ionized plasma, and while plasmas exist elsewhere in the universe, the plasma inside a white dwarf is unlike any you would find in a fusion reactor or the outer atmosphere of a star. It is not a diffuse cloud of charged particles. It is one of the densest states of ordinary matter that can exist without collapsing into something even more exotic, like a neutron star. Because the nuclei have no electron clouds around them, they are naked. They interact with each other directly through their positive charges. There is no shielding, no cushion, no chemistry. When two carbon nuclei get close, they feel only one thing about each other: electrical repulsion. Same for two oxygen nuclei, or a carbon and an oxygen. The only reason they do not simply fly apart from each other is that they are packed too tightly, held in place by the enormous crushing pressure of everything above them. They are also constantly being jostled by heat, which we will come back to in a moment. But at any given instant, each nucleus is essentially asking every other nucleus in its neighborhood to please move aside. Now think about the electrons. In an ordinary metal, like the copper in a wire, electrons are somewhat free to wander through the lattice of atoms, but there are still only a few of them per atom, and they behave in ways that are still mostly explainable using Newtonian intuition. In a white dwarf's interior, the electron density is staggering, and the electrons are behaving in a way that has almost no everyday analog. They are degenerate. That word we introduced earlier is worth expanding on now that we are looking at them up close. Degenerate does not mean broken or corrupted. It is a technical term meaning that the electrons have been packed together so tightly and forced into so many different momentum states that quantum mechanics is calling the shots on how they behave, not temperature. Every electron here has been forced into some specific quantum state, and no two of them are allowed to be in the same state. That is the exclusion principle again. In a normal gas, temperature dominates. Particles zip around with a range of speeds set by how hot the gas is, and the vast majority of possible quantum states are unoccupied. In this degenerate electron sea, almost every low-energy quantum state is already taken. If you want to add another electron or move an existing one, you have to send it into a very high-energy state because all the low ones are full. The result is that these electrons are moving fast, extraordinarily fast. Some of them at appreciable fractions of the speed of light, not because the plasma is hot enough to accelerate them, but because there is simply no room for them to be slow. Even if you could somehow cool this material to absolute zero, the electrons would still be racing. They would still be exerting pressure. That is the pressure that holds the whole star up. There is a concept worth pausing on here, because it will help everything that follows make sense. Physicists call it the Fermi energy, and it is the energy of the fastest moving electrons in the degenerate sea, the ones that have been forced into the highest occupied momentum states, because all the lower ones are taken. In an ordinary gas, if you cool the material down, all the particles slow down together, and their energies drop towards zero. In a degenerate electron sea, no matter how much you cool the material, the highest energy electrons cannot slow down. The lower states are full, and the exclusion principle will not let them settle. The Fermi energy stays put. This means that in a very real sense, the electrons inside a white dwarf have a kind of built-in floor to how cold they can ever get. Even if the temperature dropped to almost absolute zero, most of the electrons would still be racing along with enormous energies, providing enormous pressure, holding the star up as vigorously as ever. Temperature for these electrons is almost irrelevant. They are locked into their behavior by geometry and by counting, not by heat. This is a strange thing to swallow, because your intuition wants to say that cooling something always slows it down. In this material, cooling barely touches the electrons. It only touches the ions. And that is why the entire drama of crystallization plays out among the ions, in the arrangement of the nuclei, while the electrons continue their unchanged quantum roar in the background. The two populations are, in a sense, living in different worlds inside the same star. So, picture what surrounds you now. A landscape of bare, positively charged nuclei, spaced fairly evenly because they repel each other, and a smooth blur of ultra-fast electrons filling every gap, providing the invisible pressure that keeps the whole ocean from collapsing. There is no clear separation between the two. The electrons are not orbiting anything. They are everywhere at once, a quantum mechanical fluid that permeates the entire interior. If you tried to lift a scoop of this material out with a cosmic ladle, you would find it impossible, because the electron pressure that holds it up here would explosively decompress the moment you release the containing gravity. What looks stable at these depths would erupt violently at any lower pressure. This material is not a substance in the way rock is a substance. It is a state that only exists because everything around it is squeezing on it just right. At this point, it is worth spending some time on what hot really means down here, because the word is about to become very slippery. If someone tells you the temperature at the center of a young white dwarf is around 10 million degrees, your first instinct is to think of an inferno. an unimaginable furnace that would incinerate anything you tried to send into it. And in a sense, that instinct is correct. The temperature is real. It measures the average energy of random motion of the particles. But here is the subtlety. In ordinary matter, that random motion controls almost everything. In a warm balloon of gas, temperature tells you how fast the molecules are bouncing, how much pressure they produce against the walls, what phase the substance is in, whether it will hold together as a liquid or fly apart as a vapor. Temperature is king. Inside a white dwarf, temperature is not king. It is a courtier. It matters, it participates in the story, but it is not the most important variable in the room. That title belongs to density and to the forces that density unlocks. When you cram positively charged nuclei this close together, the electrical repulsion between them becomes an enormous factor in what they do next. Even a very hot nucleus, being jostled by thermal energy, cannot forget the powerful nudge it is getting from every neighbor around it. Temperature says, keep moving randomly. Repulsion says, stay out of my personal space. Under normal conditions, temperature drowns out repulsion. Under white dwarf conditions, they are in a fair fight, and as the star cools, the fight tips. To help this intuition along, think about salt water. If you dissolve a spoonful of salt in a glass of warm water, the sodium and chloride ions float around freely, jostled by the thermal motion of the water molecules, essentially indifferent to each other's presence, except in a very loose statistical sense. Now, imagine that you could magically shrink the water down until the ions were shoulder to shoulder, so densely packed that each one was almost touching its neighbors. Suddenly the ions can no longer ignore each other. Their electric forces become important. Their positions are no longer random. Even at the same temperature, they are behaving very differently. Because now density has given the electric forces a chance to speak up. That, in essence, is what happens inside a white dwarf. The density is so extreme that the electric conversation between neighboring nuclei is loud enough to be heard over the thermal noise. Not loud enough yet to shut the thermal noise down completely. Not in the young, hot phase we are looking at now, but loud enough to matter. Loud enough to prepare the way for something remarkable. For now, in the young white dwarf, the nuclei are still jostling around freely. They have preferred spacings from each other. They feel each other's charge, but thermal energy is still winning the argument. They wander, they slide past each other, they do not stay in any particular arrangement. This is what physicists mean when they say the interior behaves as a liquid plasma. Not liquid in the sense of a puddle you could splash your foot in. Liquid in the sense that the particles are dense, in contact with their neighbors in a meaningful way, but still free to flow past each other. The nuclei are not locked into any grid. They can rearrange themselves. If you could somehow watch this on a microscopic scale in slow motion, you would see a shimmering, chaotic dance, each nucleus surrounded by a rough halo of others, at a preferred distance, but the identities of the neighbors constantly swapping as the whole ocean stirs itself with thermal motion. Notice how strange this liquid is compared to any liquid you have encountered. Water is a liquid because the hydrogen bonds between its molecules are strong enough to keep them clumped together, but weak enough to let them slide. Molten iron is a liquid because the metallic bonds between its atoms are strong enough to hold, but heat gives the atoms enough energy to flow. The white dwarf's ionic liquid is bound together by nothing so gentle. Its liquidness comes from the fact that the density is high enough to pack the nuclei against each other, but the temperature is high enough that they still overcome each other's electrical resistance. If you could somehow freeze this material in place and pull it out, it would not be a viscous fluid. It would be a stiff, glassy, ultra-dense material that most laboratories could not even measure. But in situ, inside the star, it flows. This is a crucial word to get right. The ocean flows. Heat flows through it. Currents can develop within it. Because the electrons form a highly conductive sea, essentially a superhighway for energy transport, heat moves through the interior of a white dwarf far more efficiently than it moves through most ordinary materials. That is why the interior is so nearly the same temperature everywhere except in the outer layers. The core does not have a sharp thermal gradient like the sun does. It is more like a giant thermally connected block, with almost every part of the interior at nearly the same temperature. All the resistance to heat flow, all the throttle on the star's rate of cooling, sits in that thin atmospheric envelope on top. The interior of a white dwarf is like a massively insulated pot with a very thin lid. The pot is enormous, filled with hot fluid, and the lid is what slowly lets the heat escape. That property controls the star's evolution. It is why white dwarfs cool over billions of years instead of centuries. The reservoir of stored heat is titanic. The rate at which it can leak out through the outer skin is small. So the star glows and glows and glows, gradually fading as its interior gives up warmth to the envelope, which radiates it as light. The interior does not brighten or flicker. It just quietly cools over spans of time that dwarf the age of civilizations. Now, we should be careful with one more piece of language, because it comes up all the time and it is misleading. When you hear that a white dwarf is cooling, it is easy to imagine the star burning down like a log in a fireplace, its heat coming from some active combustion that is running out. That picture is wrong. There is no combustion. There is no fusion. Nothing is being consumed at the core to generate warmth. The heat in a white dwarf is not being produced. It is being remembered. Every joule of thermal energy in that interior was already there when the star first became a white dwarf. Some of it is left over from the last fusion reactions that occurred just before the star retired. Some of it comes from the gravitational contraction that shaped the core in the first place. But once the white dwarf has formed, no new fuel is being burned. The star is simply spending down a bank account of stored heat. The interior does not know or care that fusion has stopped. It just holds its energy and slowly leaks it away. If you find the image strange, think about a piece of iron freshly pulled from a forge. It comes out orange and glowing, and if you leave it on an anvil, it will slowly turn dull red, then black, then room temperature grey. Nothing is burning inside it. The metal is not producing heat. It is releasing the heat it already contained back into the surrounding air. A white dwarf is doing the same thing, on a scale that is almost impossible to picture and over a time span that dwarfs anything human. It is a cosmic ember cooling in the dark of the universe, and the darkness is patient enough to let it take its time. But even as we say the ember is cooling, we should remember what cool means at these depths. A young white dwarf can have a central temperature of a few tens of millions of degrees. An older one might have dropped to around 10 million. A very older one might be down to a few million. These are still numbers that would sound absurd if you use them anywhere else in physics. 1,000,000 degrees is unimaginably hot by our everyday standards. It is hotter than the surface of any main sequence star, hotter than most of the material in the sun outside its very core. And yet, in this bizarre corner of physics we are exploring, 1,000,000 degrees is on its way to being cold enough. Cold enough for something remarkable to happen. Cold enough for the balance between thermal motion and electrical repulsion to start slipping toward the repulsion side. Cold enough that the ocean of ions is not going to stay a liquid forever. Before we get to that moment, we need to nail down the tension that drives the whole story. Imagine in your mind that you're watching the interior of a middle-aged white dwarf. The nuclei are packed tightly, jostled by heat, feeling each other's electric fields. Every nucleus wants to be as far as possible from every other nucleus, because they all repel each other, but they cannot get far because they are all crushed together by gravity. So instead, they settle into a compromise. They arrange themselves so that on average, no two nuclei are closer than some preferred distance. If you drew a snapshot of their positions and connected each nucleus to its nearest neighbors, you would not see a regular grid. You would see a pattern that looks almost like a grid, blurred out by constant motion. Each nucleus has a sort of ghostly cage of neighbors around it, but that cage is fuzzy, and the nucleus itself is wandering. The electrostatic repulsion is trying to sharpen that cage. It is trying to force each nucleus into a specific position relative to its neighbors to reduce the total electrical energy of the system. Thermal motion is trying to blur the cage. It is trying to shake each nucleus loose from its preferred position, to give it enough energy to wander freely. Every point in the star's interior is the site of this ongoing tug of war. And as the interior slowly cools, the thermal side of the tug of war weakens. The nuclei have less energy to wander with. The electrical side, which does not depend on temperature, holds firm. Bit by bit, region by region, the balance tips. Physicists have a name for the parameter that tracks this balance. It is called the Coulomb coupling parameter, and although we do not want to bury the story in equations, the concept behind it is simple and worth understanding. It is essentially a ratio between two energies: the electrical repulsion energy between neighboring nuclei and the thermal energy that the nuclei have to move around with. When the ratio is small, thermal energy wins, and the nuclei behave as a wandering liquid. When the ratio is large, electrical energy wins, and the nuclei are trapped in specific arrangements relative to each other. When the ratio crosses a certain threshold value, the material undergoes a phase transition. It goes from being a strongly coupled liquid to being a crystal. The exact value of that threshold has been worked out by decades of laboratory-style calculations, dense plasma experiments, and numerical simulations. It sits somewhere around 175 in the units astrophysicists use. Below that number, the ions can flow. Above it, they lock into an ordered pattern. And here is where the whole hot solid mystery begins to make sense. The threshold has almost nothing to do with achieving what we would call a cold temperature. It is a statement about a balance. In a low-density gas, you would need to lower the temperature to almost absolute zero to reach the threshold, because the electrical energies at low density are tiny. In a white dwarf's core, the electrical energies are so gigantic that the threshold is reached while the temperature is still in the millions of degrees. The nuclei do not have to be cold in any earthly sense. They just have to be cold compared to how strongly they are repelling each other. This is the point that most casual descriptions of white dwarfs miss. When you hear that a white dwarf is freezing, it does not mean it has become cold. It means it has reached a specific balance between temperature and interparticle force, a balance that at ordinary densities would indeed require intense cold, but at white dwarf densities is compatible with temperatures that would vaporize any known material. This is why we said at the very start that a white dwarf does not crystallize despite being hot. It crystallizes because temperature cannot be understood separately from density and force. In the everyday world, temperature is a good proxy for how much motion a substance has and how organized it is. In extreme matter, temperature is only part of the story. The other, larger part is the strength of the interactions between the particles. Everything we have set up so far, the naked nuclei, the degenerate electron sea, the strange liquid state, the thermal reservoir slowly leaking away through the atmospheric skin, the tug of war between electrical repulsion and thermal chaos, has been building toward a single moment. That moment is the crossing of the threshold. It is when a specific region of the white dwarf's interior, most likely the very densest region at the center, first tips the balance in favor of order. The nuclei there stop being able to wander. They settle into their preferred positions relative to their neighbors, and they stay there. A new phase is born. A crystal begins to grow in the belly of a dead star. To watch that crystal form, to understand where it starts, how it spreads, how the carbon and oxygen sort themselves out during the freezing, and how this process quietly releases energy that changes the whole star's cooling history, we need to leave the ocean of ions and step into the freezing itself. That is where the story becomes truly strange. Because what forms in there is not a diamond, not a rock, not any solid you have ever touched. It is something the universe can only build inside the corpses of stars, and it is one of the largest ordered structures nature knows how to make. Somewhere in the very center of the white dwarf, at the point where the pressure has climbed higher than anywhere else in the star and the density has reached its absolute peak, the tug of war finally tips. For billions of years, thermal chaos has been winning, keeping the naked carbon and oxygen nuclei jostling through their dense ocean, sliding past each other, never settling. Now, imperceptibly at first, the thermal side loses ground. Enough heat has bled outward through the star's thin skin. Enough energy has been given up to the cold darkness of space. In the tiny volume at the geometric heart of the star, the electrical repulsion between neighboring nuclei has finally grown loud enough to shout down the noise of thermal motion, and a phase transition begins. Not the phase transition you know from your kitchen. This is not water freezing into ice, not steam condensing on a mirror, not molten wax hardening into a candle. Those familiar transitions happen because of chemical bonds forming, because molecules stop having enough energy to break free from each other's electron shells. There are no electron shells here. There are no molecules. There is not even chemistry. What is happening at the center of this white dwarf is a purely electrical phenomenon. The nuclei have simply stopped being able to overcome each other's repulsion. Each one has finally been forced to stay put relative to its neighbors. And put is not random. Put is a specific pattern, a geometric arrangement, the same one over and over, extended in 3 dimensions. A lattice is forming. To picture what that means, forget everything you know about diamond, salt, quartz, or any other crystal you have ever seen. What is condensing in the belly of this dead star is a Coulomb crystal, a solid held together not by chemical bonds, not by shared electrons, but by the pure electrical repulsion between naked nuclei. Each carbon or oxygen nucleus sits at a specific point in space, because that is the point where it feels the least total force from its neighbors. Move it slightly in any direction and the repulsion from one side of its cage becomes stronger than the other, pushing it back. It is trapped, not by attraction, but by mutual pushing. Imagine a group of people in a small room, all trying to stand as far as possible from everyone else. Eventually they distribute themselves at regular intervals, each one at the maximum distance from all the others. Now imagine that room is packed to the walls with such people, and you extend the picture outward endlessly. Each person is locked in place by the fact that every direction they might move is already occupied by someone else pushing back. That is the geometry of the Coulomb crystal. The specific arrangement that these ions settle into, in most physicists' best models, is what is called a body-centered cubic lattice. Picture a simple cube with a nucleus at each corner, and one more nucleus sitting exactly at the center of the cube. Now, repeat that cube in every direction, sharing corners with its neighbors. You get an endless three-dimensional grid of nuclei, each one equidistant from a specific set of neighbors, each one in a position that minimizes the electrical energy of the whole. That is the structure that theoretical calculations and computer simulations point to as the preferred arrangement for a strongly coupled Coulomb crystal of this kind. It is not the only possibility, and the exact structure may vary a little depending on the mixture of carbon and oxygen, but a body-centered cubic pattern is the workhorse of the models. Now, this word lattice is important. It does not mean the nuclei are welded into position, frozen absolutely still. Even in the coldest, purest crystal you can imagine on Earth, the atoms are constantly vibrating around their preferred positions with a residual quantum jitter. In the white dwarf's crystal, the ions are vibrating too, and quite vigorously by everyday standards, because the whole thing is still at a temperature of millions of degrees. The distinction between the liquid state and the solid state here is not that the ions have stopped moving. It is that they no longer move away from their assigned positions. They oscillate, but they oscillate around a fixed point. A given carbon nucleus in the solid region is now defined by its address in the lattice. It may wobble a little around that address, but it does not pack up and leave for a different address. Compare that to a moment earlier, when the same nucleus was drifting through the liquid, changing neighbors constantly. The transition from liquid to solid, in this exotic material, is really the transition from wandering to staying. Now, let us not forget the electrons. In an ordinary crystal on Earth, when atoms lock into position, their electrons often lock in too, forming specific bonds between specific pairs of atoms. That is what makes diamond a diamond. In a diamond crystal, each carbon atom is chemically bonded to 4 neighbors, and its electrons are largely tied up in those bonds. The whole structure is stiff because breaking any of those bonds requires a lot of energy. There are no such bonds in the white dwarf crystal. The electrons remain in their degenerate quantum sea. They keep swimming through the whole interior, keep carrying heat, keep providing the pressure that holds the star up. They are not attached to any particular nucleus. They are not sitting in bonds. They are the same wild fluid they were before crystallization began. What has changed is only the behavior of the ions. The electrons keep flowing, keep exerting their quantum pressure, keep making the material extraordinarily good at conducting heat. The lattice sits inside their sea like an ordered flotilla of ships, in a turbulent ocean. This is one of the key distinctions between the exotic crystal at the center of a white dwarf and any solid you have ever handled. In an Earth crystal, the electrons help define the shape. In a white dwarf's Coulomb crystal, the electrons are basically a separate system that flows around and through the lattice without caring where the lattice is. The two coexist, they interact, but the electrons do not lock into the crystal structure. If you could somehow enter this region and travel with the electrons for a moment, the crystal would seem almost invisible to you, just a smooth backdrop of positive charge. Only the nuclei know they are frozen. Now consider what is happening at the boundary of the growing solid region. In the very heart of the star, deep at the center, the crystal has begun. Move outward from that center by a few kilometers, and the density drops slightly. The pressure drops slightly. The electrical energy scale drops with them. Right at the surface of the growing crystal, the balance is a knife edge. The ions right there are barely on the ordered side of the threshold, while the ions just above them, at slightly lower density, are still on the disordered side. As the star continues to lose heat, that boundary creeps outward. The threshold crossing moves radially, layer by layer, taking material that was just seconds ago a strongly coupled liquid and locking it into the growing lattice. The solid core grows. It is a slow crystal. This is not a moment. This is not a snap freeze. The crystallization of a white dwarf is a process that unfolds over hundreds of millions of years, sometimes billions, because the star's cooling itself is that slow. Every increment of crystal growth requires the interior to have shed a corresponding amount of heat, and the star can only shed heat through its thin outer envelope. So the growth of the crystal is throttled by the atmosphere in the same way that the star's total cooling is. It is a patient process, geologically slow by the standards of any world would weather, but it is inexorable. Once the center has crossed the threshold, the freezing continues, one shell of material after another, moving outward through the ages. Not every white dwarf begins this process at the same time in its life. The mass of the star matters enormously here. A more massive white dwarf has a much stronger gravity, which means the interior is compressed to a higher density. Higher density means the electrical repulsion between nuclei is even more powerful for a given temperature. So a more massive white dwarf can cross the crystallization threshold much earlier in its cooling history at a much higher temperature than a less massive one. In practice, this means the crystallization of massive white dwarfs begins while they're still relatively bright, still relatively young. Lower mass white dwarfs have to wait longer, cool further, before their central densities are enough to force the freezing to begin. This mass dependence is important. It is one of the observable signatures that we will use later to detect crystallization happening in real stars. Now, let us come to the messy business of composition. Up to this point, we have been imagining the ions of the plasma as a single population, all being frozen together, all locking into the same lattice. But the interior of a white dwarf is not made of one element. It is made of carbon and oxygen mixed together in some ratio that depends on the parent star's evolution. The precise ratio varies from star to star, from center to surface, from model to model. There is uncertainty in the details, and physicists are still refining exactly how much of each ingredient should be present at each depth. But whatever the mixture, both elements are there. and both are subject to freezing. Here is where something remarkable happens. The two species do not freeze together in equal proportions. When you cool a mixture of two different ionic species in a plasma like this, the solid phase and the liquid phase do not have the same composition as each other. It is like what happens when you cool seawater. The ice that forms is not salty like the surrounding brine. It is nearly pure water, and the salt stays behind, dissolved in the remaining unfrozen liquid, which becomes saltier. A similar thing happens here, but with carbon and oxygen instead of water and salt. The details depend on the exact phase diagram, which is the subject of ongoing research and refinement. But the general finding is that under conditions typical of a carbon and oxygen white dwarf core, the freezing process tends to prefer oxygen in the solid phase. The nucleus of oxygen has a higher charge than the nucleus of carbon, and in the crystallization process, higher charge ions are more strongly bound by the electrical forces that define the lattice. The result is that the crystal that forms is enriched in oxygen compared to the surrounding liquid. Some of the carbon that used to be there is left behind, floating in the shrinking liquid ocean. Now think about the implications. An oxygen-rich solid is denser than a carbon-rich liquid. Oxygen has more mass per unit charge, more mass per nucleus. When a shell of oxygen-enriched crystal freezes at the boundary of the growing solid core, it is denser than the material surrounding it. Meanwhile, the remaining liquid nearby, having given up some of its oxygen to the crystal, is now relatively richer in carbon. That carbon-rich liquid is less dense than the oxygen-rich solid beneath it. And in a gravitational field, denser material sinks and less dense material rises. What follows is a slow but significant redistribution of the star's composition. The oxygen-enriched crystallized material accumulates toward the center. The carbon-enriched liquid that has been left behind is displaced upward, out of the crystal-forming region, into the still liquid interior above. It is not that a shell of ice-like solid floats and a warm ocean churns beneath it. It is more subtle. It is a continuous chemical redistribution taking place inside a plasma, with heavy material settling and lighter material buoyantly rising, driven by the tiny density differences between the two phases. Do not picture this as sediment settling in a pond. Picture it as a very slow rearrangement of composition over depth, a gradual sorting of the star's ingredients as freezing takes place. Over long time scales, the white dwarf becomes more centrally concentrated than it was before. Mass gets moved inward. When mass moves inward in a gravitational field, gravitational potential energy is released. That energy has to go somewhere, and it does. It goes into heat, into the reservoir of thermal energy that the star is slowly leaking to space. In effect, the freezing process is not only rearranging the ions, it is also mining the star's gravitational field for extra warmth. This gravitational energy release is one of the reasons crystallization delays cooling in a white dwarf. Every increment of freezing that redistributes composition puts a little more thermal energy back into the interior. It is a temporary supplement to the star's dwindling heat account. It cannot last forever, because the phase separation is limited by how much oxygen is available to migrate inward. But for a substantial fraction of the star's cooling history, it makes a real difference. There is a second, separate energy release that also comes with crystallization, and this one is more familiar. It is latent heat. Every phase transition releases or absorbs energy at the boundary. because there is an energy difference between the ordered state and the disordered state. When water freezes into ice, it gives up energy. That is why a glass of ice water can sit at 0 degrees for a long time before it warms up. The phase change is absorbing energy as the ice melts. In reverse, when water freezes, it releases energy to its surroundings. The same principle applies to the exotic crystallization inside a white dwarf. Every time a shell of liquid ions transitions into the solid lattice, a small amount of latent heat is released. Over the vast mass of a white dwarf's interior, the total latent heat is enormous. This latent heat, like the gravitational energy, is added back into the interior's thermal reservoir. It temporarily slows the star's cooling by giving it something extra to spend down. Combine the latent heat with the gravitational energy released by phase separation, and you get a substantial delay in the white dwarf's cooling, a period during which the star lingers at brighter luminosities and warmer temperatures than a naive cooling calculation would predict. In other words, the star's decline is not steady. It hits a plateau, or at least a shallow bump, during the crystallization phase, and it takes longer to get faint than it otherwise would. The exact size of this delay depends on many things. It depends on the star's total mass, which sets the density profile. It depends on the ratio of carbon to oxygen, which sets phase separation efficiency. It depends on the composition of the outer envelope, which controls how quickly heat can escape. It depends on trace impurities and on how the phase separation is modeled, which remains an active area of research. Different models predict different delays, but under a wide range of assumptions, the delay can add up to 1 billion years or more for a typical white dwarf, and even longer for favorable configurations. That is a staggering effect. It means the standard cooling age of a white dwarf, calculated without crystallization physics, would be significantly off for many stars. Notice that none of this makes the white dwarf brighter in a dramatic sense. There is no flash, no explosion, no sudden increase in luminosity that would announce to the universe, crystallization has begun. The extra heat is being fed into the interior slowly, over enormous timescales, and the star's atmosphere continues to throttle its brightness the way it always has. What crystallization does is prolong the star's twilight. It stretches out the cooling curve. It gives the white dwarf more time at a given luminosity. To an external observer, a crystallizing white dwarf looks just like any other white dwarf, only it seems to age more slowly, or to accumulate in slightly higher numbers at the luminosities where the freezing is happening. That last point will matter enormously when we get to how astronomers actually detect this whole process. For now, hold on to it as a hint. Crystallization does not shout, it whispers, it changes population statistics. And that whisper is what modern telescopes have been listening for. There is one more effect worth understanding before we leave the freezing itself. When a solid region forms inside a fluid interior, it changes how mechanical disturbances travel through the star. A liquid cannot support certain kinds of wave motion, specifically shear waves, the transverse waves that involve material sliding sideways past itself. Only solids can carry shear waves. So when the crystal region grows, a new medium for wave propagation is quietly created inside the star. Anything that vibrates, anything that oscillates, will now interact with that solid region differently than it interacted with the earlier liquid interior. The crystal is not just static structure, it is a resonating body embedded within a still fluid outer star. This will turn out to be one of the most important ways that we can peek inside a white dwarf and confirm that a crystal is really there. Some white dwarfs pulsate. Their outer envelopes oscillate in specific patterns. Those oscillations travel through the interior, and their properties depend on what they encounter along the way. A liquid interior and a solid interior sound different, in the same way that a hollow bell and a solid one ring differently when you strike them. Astronomers can listen to the ringing of pulsating white dwarfs and, with careful analysis, infer whether their innards have crystallized. But that is a story we will come to shortly. Right now, we just note that the growing crystal has this property. It is not silent. It is a new drum, quietly waiting to be struck. Let us spend a moment on what this crystal is really like as a physical medium, because it is unlike anything you have ever encountered, and its properties matter for what comes next. If you could somehow probe the crystallized core with a mechanical disturbance, tap it with a hammer of unimaginable strength, the response you would get back is nothing like the response of any material you have ever tapped. The stiffness of this crystal is extraordinary, not because the bonds between its nuclei are strong in the chemical sense. There are no bonds in that sense. But because the electrical restoring force on each nucleus, when it is nudged out of position, is colossal. Try to push a nucleus slightly out of its assigned lattice site, and every neighbor around it pushes back with a force that dwarfs anything in ordinary matter. The lattice is rigid. Waves that travel through it move at speeds that on Earth would be considered relativistic for a solid, a substantial fraction of the speed of sound in the most exotic laboratory materials, and in some cases faster. And there are different kinds of waves. In an ordinary fluid, only pressure waves can travel. Compressional disturbances that squeeze the material forward and backward along the direction of travel. These are sound waves, longitudinal, and they exist in any medium that resists compression. But solids can carry a second kind of wave, called a shear wave or a transverse wave, which involves the material sliding sideways past itself. A shear wave requires that neighboring parcels of material be locked into positions relative to each other, so that when one parcel is shifted sideways, it drags its neighbors with it. A fluid cannot do this. The parcels just slide past each other and no wave forms. A solid, with its ions locked into their lattice positions, can. This is why earthquakes on Earth produce two distinct kinds of seismic waves that arrive at seismographs at different times: a fast pressure wave and a slower shear wave. The shear wave only propagates through the solid parts of the planet, and its behavior is one of the clearest ways to map out the boundaries between solid and liquid layers inside Earth's interior. The same physics applies inside the white dwarf. The moment a region of the interior crystallizes, it becomes able to carry shear waves for the first time. A new channel for mechanical energy propagation opens up. The liquid ocean above the crystal cannot carry shear waves. The crystal can. Any disturbance that reaches the boundary from above will now behave in a fundamentally different way when it enters the solid. Some of it will reflect off the boundary. Some of it will refract, changing speed and direction as it crosses. Some of the modes will convert from one type to another. The white dwarf, which used to be a uniform fluid interior surrounded by an atmospheric envelope, has become a layered instrument with a solid drumhead at its core and a liquid ocean above it, coupled together in ways that will leave fingerprints on any oscillation that runs through the whole star. let us step back and take in what has just happened. In the depths of an Earth-sized stellar corpse, over a span of hundreds of millions of years, an ocean of ions has slowly given itself up to order. The carbon and oxygen nuclei that once wandered freely are now, in the innermost regions, locked into a body-centered cubic lattice, vibrating in place but no longer drifting. The lattice is not a diamond, no matter how tempting the nickname. It shares no chemical bonds. Its electrons are not held between adjacent atoms. It is held together by naked electrical repulsion, and it is bathed in a sea of degenerate electrons that continue to flow around it. Its composition is not the same as the parent liquid. Oxygen has preferentially entered the solid, leaving the surrounding liquid slightly enriched in carbon. This has caused the star to become more centrally concentrated, releasing gravitational energy. The crystallization has also released latent heat as each layer of ions locked into place. Both energy releases have gone into the star's slowly draining thermal reservoir, delaying its cooling by anywhere from hundreds of millions to billions of years, depending on the specifics. Meanwhile, the star from the outside looks essentially the same. A little dimmer than it was long ago, perhaps a little redder, but not obviously different from a white dwarf without a solid core. There is no crust visible on the surface. There is no glittering diamond face turned to space. The atmosphere is still there, still opaque, still hiding the strange lattice below. If you pointed a telescope at this star, you would see a smooth, glowing spectrum, indistinguishable at a glance from many other white dwarfs across the sky. The revolution has taken place in absolute privacy. So how do we know it is real? How do we know that any of what we have just described actually happens? That these frozen cores exist inside real stars in real numbers? That our theoretical picture is not a beautiful fiction? For a long time, that was a fair question. The physics was worked out on paper decades ago, but confirming it in the real universe required tools that did not yet exist. Astronomers had to figure out how to detect a phase transition happening inside an invisible core, through a thick, opaque atmosphere, hundreds of light years away. They had to find the whisper. They found two whispers, actually. One came from staring at millions of white dwarfs at once and noticing that they were piling up in a very specific place on a cooling diagram, exactly where models had predicted crystallization would slow them down. The other came from listening to the ringing of individual pulsating white dwarfs, where the vibrations betrayed the presence of a solid interior. Together, these observations turned the crystallization theory from a beautiful piece of dense matter physics into a confirmed feature of real stellar death. To hear those whispers and to understand what they revealed about the deep future of every dying star like our sun, we now leave the freezing itself and step into the astronomer's chair. The stage is set. The instruments are waiting. And the invisible crystal, buried in the dead heart of a distant star, is quietly whispering to anyone with the right ears to listen. The interior of a white dwarf is invisible. Nothing in the light coming from that atmosphere is a snapshot of the crystal core. Nothing in any spectrum shows the lattice directly. Between the outside universe and the frozen heart of the star lies thousands of kilometers of opaque plasma, thick enough to swallow every photon that tries to escape from within. A photon born at the surface of the growing crystal is not going to reach anyone's telescope. It is going to be absorbed almost immediately, its energy shuffled through countless interactions in the overlying material, until whatever eventually emerges at the surface has forgotten everything about where it started. The star's atmosphere is a sensor. Whatever the crystal is doing, the crystal has to say it in some other language. And yet, astronomers know the crystal is real. They cannot see it, but they have caught its fingerprints in two very different ways. And the two ways corroborate each other so cleanly that the case has moved from elegant theory to confirmed feature of stellar death. One of these fingerprints comes from mapping a huge population of white dwarfs at once, and looking for statistical bumps where the models say the freezing has to slow the cooling down. The other comes from listening to individual white dwarfs that happen to vibrate, and reading the frequencies, their oscillations, for hints that the innards have become solid. The first fingerprint required a spacecraft that could measure the distances to 1 billion stars. The second required patient decades of watching a handful of pulsating stars flicker in the darkness. Together they turned an invisible process into a matter of observational fact. Start with the population evidence, because that story has a very clear beginning. About a decade ago, the European Space Agency launched a small spacecraft into a stable orbit around a gravitational balance point past Earth's night side. Its job was almost absurdly ambitious. It was going to build the most precise three-dimensional map of the Milky Way ever attempted. It would spin slowly on its axis, scan the entire sky over and over, and pinpoint the position, brightness, motion, and color of nearly 2 billion stars. That spacecraft was called Gaia, and its data has quietly rewritten large portions of stellar astronomy over the last several years. For the crystallization story, the crucial thing Gaia provided was precise distances to white dwarfs. Before Gaia, distances to white dwarfs were mostly rough estimates. You could pick a few nearby ones, measure their parallax carefully with early emissions, and get a decent number, but for the general population, you had to guess. And distance is essential. Without a good distance, you cannot convert a white dwarf's apparent brightness in the sky into its true luminosity. Without a true luminosity, you cannot place it accurately on a diagram of luminosity versus color, which is the diagram astronomers use to track how stars evolve. And that diagram, called the color magnitude diagram or the Hertzsprung-Russell diagram, depending on how you draw it, is the map on which the whole story of white dwarf cooling is written. A white dwarf slides down its cooling sequence from upper left to lower right on this diagram. It starts hot, bright, and blue-white in the upper left. As it loses heat, it fades and reddens, moving toward the lower right. If cooling proceeded at a perfectly steady rate the whole way down, you would expect white dwarfs to be spread more or less evenly along the sequence, thinning out gradually as the older ones become too faint to see. That is not what Gaia found. When astronomers plotted tens of thousands of nearby white dwarfs with Gaia's precise distances, they saw something odd. There was a distinct pileup. A specific region of the cooling sequence contained more white dwarfs than a smooth cooling model predicted. The stars were bunching up there, as if they were slowing down as they passed through that section of the diagram. Bunching up meant lingering. If more stars are found at a particular luminosity than at higher and lower luminosities, it is because they spend more time at that luminosity. Something is delaying their descent, holding them in place, keeping them from becoming fainter as quickly as the naive models predict. And when astronomers compared the location of the pileup with the predictions from crystallization models, the match was compelling. The pileup sat right where the models said the phase transition, along with carbon and oxygen separation, should be depositing extra energy into the cooling white dwarfs. There it was, hiding in plain sight in a diagram that astronomers had been drawing for a century. The freezing was slowing the stars down, exactly as the theory said it should. The delay was long enough, and the delivery of extra energy was concentrated enough at specific temperatures that it left a visible bump in the population. Even better, the location of the pileup varied with mass. More massive white dwarfs, whose greater gravity compresses their interiors to higher densities, are supposed to begin crystallizing at higher surface temperatures than less massive ones. When astronomers separated the Gaia white dwarfs by their masses, the pileup shifted along the cooling sequence in exactly the way that theory predicts. The heavier ones piled up at brighter luminosities. The lighter ones piled up at fainter luminosities. This was not one lucky coincidence. This was a systematic, mass-dependent signature that matched the crystallization hypothesis in detail. It would have been extraordinarily difficult to fake. It would have been extraordinarily unlikely as a coincidence. It was almost certainly the fingerprint of a real phase transition happening inside real stars. It is worth being careful about what this evidence shows. Gaia didn't photograph a single crystal, didn't resolve the interior of a single white dwarf. What Gaia did was measure positions and brightnesses of a huge sample of nearby white dwarfs so precisely that when those numbers were combined with theoretical cooling models, a subtle statistical bump became detectable. This is population-level evidence. It leans on the models to interpret, but the shape of the bump, its location, and above all its dependence on stellar mass are so specific to crystallization physics that most astronomers now regard it as very strong evidence indeed. In science, this is often what a confirmation looks like. Not a photograph, but an unmistakable statistical fingerprint that could not easily arise from anything else. The Gaia pileup is one whisper. The second whisper comes from a completely different direction, from a small number of white dwarfs that happen to vibrate in the darkness. These are the pulsating white dwarfs, and they are one of the most useful gifts nature has given to stellar physicists. Not every white dwarf pulsates. Only certain ones, at certain stages of their cooling, undergo natural oscillations in their outer envelopes. When they do, they periodically brighten and dim by small amounts as different regions of their surfaces heat and cool in synchrony with the underlying vibrations. A patient astronomer with a good telescope and a stable clock can measure these tiny brightness changes over long stretches of time and infer the exact periods and amplitudes of the star's oscillation modes. Each oscillation mode is a specific pattern of vibration that runs through the star. Some modes involve waves traveling near the surface. Others plunge deep into the interior, probing regions that no direct measurement could ever reach. The frequencies and shapes of these modes depend sensitively on the internal structure of the star, on the density profile, on the composition gradient, on the location of any sharp boundaries. Analyzing the pattern of oscillations to infer internal structure is called asteroseismology, and it is one of the most powerful indirect probes in all of stellar physics. It is essentially the astronomy of listening. Instead of looking at the star, you listen to how it rings, and you deduce what is inside from the notes it plays. Not every mode is audible in a literal sense, of course. What astronomers actually measure is light, the small periodic changes in the star's brightness, but the principle is the same as listening to a bell. When you hit a bell, its sound depends on its shape, its material, its size, whether it is solid or hollow. whether it has cracks. Different bells make different sounds. A white dwarf is the same. A liquid interior rings differently from a solid interior. If part of the star is crystallized, the wave modes that penetrate that region will behave differently from what they would in a fully liquid star. Their periods will shift. Their amplitudes will change. Some modes may become forbidden, unable to propagate through the solid at all. Others may appear that would not exist without the solid boundary. This is where a specific star, catalogued as BPM 37093, enters the story as its most celebrated individual example. It is not the closest white dwarf, not the brightest, not the most spectacular in any obvious visual way. What makes it special is its combination of properties. It is unusually massive, which means its interior density is high, which means it can begin crystallizing while it is still hot enough to pulsate. Many other pulsating white dwarfs are lower mass, less compressed, and either have not begun crystallizing or have finished crystallizing so long ago that they are no longer in the pulsation phase. BPM 37093 sits right in the sweet spot, massive enough to be freezing right now, hot enough to still be ringing. And so astronomers have watched it for years, watched its brightness modulate with the deep vibrations of its interior, and used those vibrations to sound out its guts. When the results of these observations were first compared with theoretical models, the picture that emerged was striking. The oscillation frequencies of BPM 37093 fit best with a model in which a substantial fraction of the star's mass was already crystallized. Some early analyses suggested that a very large fraction of the star's mass, potentially the majority, was already in the solid phase. That result was so evocative, so easy to picture, that it captured public imagination in a way that most technical stellar physics never does. Somebody at some point looked at that number and the composition and the geometry and coined the phrase that would define the star in the popular mind for the rest of its existence. They called it a diamond in the sky. The nickname spread like fire. BPM 37093 was rechristened by science writers, blogs, and headlines, and given the affectionate name Lucy, an homage to a certain famous song about a girl in the sky. And the story became irresistible. A dead star, only a few Earth radii wide, thousands of light years from us, quietly turning into a giant gemstone. It practically writes itself. It is the kind of image that leaps off the page and lodges itself in memory. And it is not entirely wrong. There really is a crystallized core. It really is made largely of carbon and oxygen. It really is one of the largest solid structures the universe knows how to build. Everything about the image touches something real. But everything about the image also misleads, and this is where it is worth being scrupulous, because the beauty of the truth is more interesting than the beauty of the metaphor. Let us take apart the diamond nickname carefully. A diamond, in the ordinary sense of the word, is a very specific kind of crystal. It is made of pure carbon, held together by covalent bonds between adjacent atoms, arranged in a specific geometry that gives the material its extraordinary hardness and optical properties. Every carbon atom in a diamond has 4 neighbors, and it is chemically bonded to each of them, sharing electrons in ways that give the whole structure its rigidity and clarity. Diamonds form under high pressure and moderate temperature in the mantle of a planet like Earth. And once formed, they persist in a stable configuration that can be cut, polished, and worn on a finger. Now compare that to the crystal at the heart of a white dwarf. It is not made of pure carbon. It is a mixture of carbon and oxygen, with the mixture depending on the star's history, and with the composition varying with depth due to the phase separation we described. Its bonds are not covalent. There are no chemical bonds at all. The electrons in the interior are not tied up between pairs of nuclei. They are in a common quantum sea, permeating the whole material. The lattice geometry is not the tetrahedral structure of diamond. It is a body-centered cubic arrangement, held together by pure electrical repulsion between neighboring nuclei. The density is not the density of diamond, it is roughly 1,000,000 times higher. The pressure required to keep it stable is not the pressure of a planetary interior, it is the pressure of a stellar corpse. If you removed a piece of this material from the white dwarf and set it on a table, it would not stay a diamond, or anything like one. It would explosively decompress, its stored pressure blasting apart the moment the surrounding gravity was gone. There is no gem here to steal. There is no jewel to cut. The crystal exists only because the star exists around it, holding it in place with its own weight. And yet the word diamond carries so much affection, so much cultural weight, that people love to run with it. There are headlines that convert the star's mass into carats. If you calculate how much the mass of a white dwarf would weigh in carats and treat it as if it were a single gemstone, you get numbers that are unimaginably large. It sounds impressive. It also has no physical meaning whatsoever. Carats are a jeweler's unit, a shorthand for weighing something that has an established market value per gram. Nothing about the material at the heart of BPM 37093 has anything to do with jewelry. You could not mine it, could not transport it, could not shape it, could not sell it. Reducing the star to a number of carats is a fine piece of stagecraft, but it should not be taken as a real comparison. It is a hook, not a description. None of this diminishes what has actually been discovered. What has actually been discovered is more subtle and, in its own way, more astonishing than a giant jewel. It is that under the extraordinary conditions inside dead stars, ordinary matter organizes itself into a lattice that has no analog in earthly experience. That the same phenomenon of freezing, familiar from water and metal and every solid we handle, extends into a regime of pressure and density where the very idea of a chemical bond disappears. That the universe knows how to build ordered structures out of naked electrical repulsion, and that it has been doing so quietly, inside cooling stellar corpses, for as long as there have been white dwarfs to cool. Whether or not you call it a diamond, that is a marvelous truth. Estimates of exactly how much of BPM 37093 has crystallized have shifted over the years as models have improved. It is important not to attach any single percentage to the star as a settled fact. Different modeling assumptions produce different fractions. Different treatments of the outer envelope, of the internal composition, of the phase diagram of the freezing mixture, all pull the answer around. What is robust across many analyses is that a substantial fraction of the star has crystallized. The exact number is a moving target. This is a general feature of white dwarf asteroismology. It gives you extraordinary indirect access to the interior of a star, but that access is filtered through a modeling machinery whose inputs continue to be refined. The right way to talk about BPM 37093 is to say that its pulsations are consistent with a large solid core, and that our confidence in this result comes from the way multiple independent lines of theory point in the same direction, not from a single crisp measurement. Before we move on to what all of this means for our own star, there is a related process worth mentioning because it has been drawing increasing attention from researchers, and it deepens the story of how a cooling white dwarf actually releases its stored energy. It concerns a minor ingredient we have so far ignored. Alongside the carbon and oxygen nuclei that dominate a typical white dwarf, there are trace amounts of heavier isotopes inherited from the parent star's late evolution. One of the most important is a form of neon called neon-22. It is not a large fraction of the total mass, but there is enough of it that it can matter. Neon-22 has a peculiar property. Compared to carbon and oxygen, it carries slightly more mass per unit of electrical charge. This makes it, in the gravitational field of the star, a little heavier for the amount of electrical support it gets from the surrounding degenerate electrons. And that means that in the still liquid interior of a cooling white dwarf, before the freezing has locked everything into place, the neon-22 nuclei can slowly drift downward. They fall, gently, over enormous timescales, towards the center of the star. It is a form of gravitational settling, extraordinarily slow by human standards, but real and cumulative over billions of years. As the neon-22 settles toward the center, it releases gravitational potential energy, just as the phase-separated oxygen does during crystallization. That energy goes into the star's thermal reservoir. It is another supplement to the star's dwindling heat account, another mechanism for slowing the cooling. And the interesting thing is that this settling process can begin even before the crystallization front has arrived at a given depth. It is not the same as the phase separation of carbon and oxygen during freezing. It is a separate, related, gravity-driven sorting of a minor ingredient. In some white dwarfs, particularly those with unusual compositions or observed cooling delays that seem larger than latent heat alone can explain, neon sedimentation has been proposed as an additional contributor. Some more recent work has even suggested that under certain conditions, neon-rich material can undergo its own kind of distillation, separating out in ways that release still more gravitational energy than simple sedimentation would predict. This remains an active area of research, and the details are not fully settled. But it is worth knowing that the picture of a cooling white dwarf is even richer than latent heat and carbon-oxygen phase separation alone. There are quieter processes running in the background, sifting heavier isotopes toward the center, feeding thermal energy back into the interior for reasons that have nothing to do with the freezing itself. The dying star is doing more work than it first appears. Model dependence is a general feature of how astronomers confirm crystallization. The two lines of evidence, Gaia's population pileup and the asteroseismology of individual pulsating stars, carry weight because they agree with each other and with independent dense plasma calculations. The confidence in the whole picture comes from the way these independent methods reinforce each other, not from any one of them being definitive on its own. Astronomers have been appropriately careful about this, and the crystallization story is now taken seriously as an established feature of white dwarf physics, because the theoretical predictions, the population statistics, and the individual stellar rings all converge on the same answer. Now, let us clear away a few misconceptions before we look at the deep future, because certain ideas about crystallizing white dwarfs are almost irresistibly wrong, and it is worth stopping them at the door. Crystallization does not restart fusion. It does not provide the star with a new nuclear energy source, and it does not push the star toward a supernova. The energies involved in the phase transition and the associated composition changes, while impressive on the scale of what a cooling white dwarf normally has to work with, are tiny compared to the energies of nuclear fusion or of a supernova explosion. Latent heat and gravitational settling are cooling delays, not ignition triggers. A white dwarf that is partially crystallized is just a slower cooling white dwarf. It is not on some pathway to a violent event. Crystallization also does not make the star suddenly dim, does not make it invisible, and does not, in any way, form a solid crust on its surface. The freezing begins deep in the interior, at the center where density is highest, and moves outward from there over enormous timescales. The atmosphere on top of the star remains a thin plasma, glowing white or blue-white or yellow, depending on the star's temperature. If you could point a telescope at a crystallizing white dwarf, you would see essentially the same smooth spectrum you would see for a non-crystallizing one at the same temperature. The crystal is silent in visible light. It only reveals itself indirectly, through the cooling delay or through pulsation frequencies. The star also does not become solid as a whole. Even in the case of a very advanced crystallization, where a substantial fraction of the mass has entered the solid phase, there is still a liquid layer above the crystal, and above that liquid layer there is the envelope of helium and possibly hydrogen. The distinction between the crystallized region and everything else is sharp in principle, but the star as a body is still a layered object. Nobody is walking on its surface. Nothing is glittering when the light hits it. The word solid is doing important physical work when we apply it to the crystallized region, but that region is buried under thousands of kilometers of everything else. There is one more implication of all this that is worth spelling out, because it reaches beyond the individual star and into how we measure the history of the entire galaxy. White dwarfs, because they cool at a rate that depends only on their mass, composition, and internal physics, can be used as cosmic clocks. If you know how a white dwarf cools, you can look at how faint a given white dwarf has become and estimate how long it has been cooling. That gives you an age. And if you find the faintest, coldest white dwarfs in a given population, they tell you how long ago the earliest members of that population died. This technique is called white dwarf cosmochronology, and astronomers have used it to estimate the ages of star clusters, of the disk of the Milky Way, of the galactic halo, and even indirectly to constrain the age of the universe itself. Here is why crystallization matters for this whole enterprise. If you build a cooling model that ignores the delay caused by freezing and phase separation, you will systematically get the ages wrong. A white dwarf that has spent 1 billion years lingering on the crystallization plateau will look, from the outside, exactly like a white dwarf that cooled straight through in less time. Without accounting for the plateau, you might conclude that the star is much younger than it actually is, or in some cases much older, depending on where the plateau shifts your inferred cooling trajectory. This is not a minor correction. For some populations of white dwarfs, the crystallization delay is a significant fraction of the total age you would infer. Ignoring it means every derived age drifts. This has consequences that ripple outward. The age of the oldest stars in the Milky Way, the timing of ancient episodes of star formation, the history of when the disk of our galaxy assembled. All of these questions have at various times been addressed using white dwarfs as chronometers. As the underlying physics of the cooling has improved, particularly the physics of the crystallization delay and the associated phase separation, the age estimates have shifted. Not by wild amounts, but by amounts that matter for understanding when things happened in the deep past. It is a striking example of how an obscure piece of dense plasma physics, the freezing behavior of a mixture of carbon and oxygen ions at millions of degrees, ends up feeding directly into questions about the age and history of the galaxy we live in. Now, having placed all this on solid ground, we can allow ourselves to look ahead. What is going to happen next in this story, both for a typical white dwarf and for the Sun itself? The Sun will eventually leave behind a white dwarf. Its exact future depends on details of stellar evolution that continue to be refined, but the general picture is well established. In roughly 5 billion years, the Sun will exhaust the hydrogen at its core and begin the transformations we described earlier. It will swell into a red giant, burn helium in a series of episodes, and shed most of its outer material into a planetary nebula. What will be left behind is a carbon-oxygen white dwarf, roughly the size of Earth, containing perhaps half of the Sun's current mass. That naked remnant will emerge extremely hot, perhaps 100,000 degrees at its surface, glowing brilliantly blue-white against the darkness. And then, it will cool. Not quickly. For billions of years, the young solar remnant will radiate heat to space through its atmospheric envelope, sliding down the cooling sequence, growing fainter and redder. At some point, the central density will be high enough and the interior temperature will have fallen enough that the crystallization threshold will be crossed at the very center. A small, solid region will begin to form. Then, over further billions of years, that solid region will grow outward as the star continues to cool and shed heat. Carbon and oxygen will separate, oxygen moving inward as the crystal preferentially incorporates it. Gravitational energy will be released, latent heat will be released. Both will slow the cooling. This is the same story we have been telling, but now it is applied to our own star's inevitable, distant future. The saying that the Sun will become a diamond is one of those bumper sticker versions of a rich physical picture. It is true in a very limited sense. The remnant that the Sun leaves behind will eventually crystallize, but most of the Sun's current material will not be part of that remnant. It will have been blown out into the surrounding interstellar medium during the red giant and planetary nebula phases, mingling with the gas between stars, eventually being incorporated into future generations of stars and planets. Only the compact carbon-oxygen core, about half the Sun's current mass, will crystallize. And that crystallization will not happen tomorrow, or in 1,000,000 years, or in 1,000,000,000 years. It will unfold across the immensely long cooling history of a white dwarf over spans of time so vast that even the age of the current universe is only a small fraction of them. The precise timing of when crystallization begins and ends for a solar mass white dwarf depends on the models. Different assumptions give different answers, but the general timescale is measured in billions of years for the beginning of crystallization and much longer still for the completion. As the crystallization front moves outward, the star continues to cool. Its luminosity continues to drop. Its temperature continues to fall. Eventually, in the far, far future, the crystallization front will encompass most of the mass, and only the very outermost layers, the thin envelope of lighter material, will still be liquid or gaseous. Push the clock further, and we arrive at the theoretical concept of a black dwarf. A black dwarf is what a white dwarf becomes after it has cooled so much that it no longer emits any appreciable light. Its residual heat is gone. Its surface has faded to near invisibility against the cosmic background. Its crystal core has grown to encompass most of its interior. It is still a massive, dense object. It still has a gravity. It still occupies space. It just does not shine anymore. The name Black Dwarf is a poor one, because it invites confusion with a black hole, and the two have almost nothing in common. A black dwarf is not a singularity. It has no event horizon. It is an old, cold, solid stellar remnant that has simply run out of light. It has structure, it has mass, it has geometry, it just no longer emits. Here is the striking part. No black dwarf currently exists in the universe. The universe is not old enough. Even the oldest white dwarfs, formed shortly after the first stars died, have not had time to cool to that state. The cooling timescales for reaching black dwarf temperatures are enormously longer than the current age of the universe. Every white dwarf we see today, no matter how ancient, is still visibly glowing to some extent. The transition from a white dwarf to a black dwarf is a prediction about the deep future, not a description of anything in our sky. When we say a white dwarf will eventually become a black dwarf, we are talking about a fate scheduled for a universe far older than the one we live in. Try to hold that timescale in your mind for a moment. The universe is currently about 14 billion years old. That is the entire span of cosmic history so far. From the earlier structure formation, through the birth and death of countless generations of stars, through the assembly of galaxies, through the formation of planets and the emergence of life on at least one of them. All of that fits inside 14 billion years. The time required for a typical white dwarf to cool to black dwarf temperatures is not measured in tens of billions of years. It is not measured in hundreds of billions. It is measured in something much longer, plausibly in the trillions or quadrillions of years, so long that the current age of the universe is essentially a single instant at the beginning of the process. To reach the black dwarf state, a white dwarf has to shed nearly all of its stored thermal energy through the trickle allowed by its outer envelope. That trickle is slow to begin with, and it becomes slower as the star gets colder, because the rate of energy loss depends on how much heat there is to radiate. As the star cools, its cooling slows, and slows again and slows again. It is an asymptotic approach to darkness that never quite gets there in any finite time you can easily picture. The end state is a limit, not a destination, and the universe would have to be many orders of magnitude older than it currently is for any real white dwarf to have gotten there. Which means that when we describe the black dwarf, we're describing a future the universe has not yet reached, and might never reach in any simple, straightforward way. It is a prediction about matter, about the physics of cooling degenerate objects, extrapolated forward far beyond anything we can observe. It is what happens if you leave the physics running long enough, and the universe holds together long enough to let it run. This last piece is what makes the whole story feel almost too big to hold. The white dwarfs cooling right now, some of them crystallizing right now inside their cores, are moving toward an end state that no member of their species has yet reached. They are pioneers of the deep future, running the clock forward on cosmic timescales, showing us in slow motion what will eventually happen to every star like ours. The sun, when its time comes, will join them, and its remnant will crystallize, delaying its own cooling by some fraction of the future, before drifting on toward the same distant black dwarf endpoint that awaits all of them. Every ordinary sun-like star, if left undisturbed, ends this way. Not with a bang, not with an explosion, but with a slow, patient freezing over spans of time that dwarf everything human. A dying star that seems inert, extinguished, done with its story, turns out to have one more transformation to accomplish. Deep in its interior, over ages we cannot easily picture, it is still changing. It is turning to stone. And in doing so, it is teaching us that the death of a star is not the end of physical change. It is only a quieter form of it. There is something profound about that. The universe does not stop with the extinguishing of nuclear fires. The corpse of a star keeps working, keeps reorganizing itself, keeps releasing tiny amounts of energy through processes that unfold across billions of years. The end state of an ordinary star is not a dead cinder. It is a slowly crystallizing, slowly cooling structure, one of the largest single-ordered objects the universe knows how to make. It is not a diamond in the sentimental sense of the word, but it is something better. It is a lattice of naked nuclei held together by pure electrical force, bathed in a quantum ocean of electrons, sitting at the geometric heart of an ember that once fused hydrogen. It is a monument to the deep patience of physics, and it is the future waiting quietly for every star like our sun, including the one that keeps us alive today.